Moniuni, I know you're recording the meeting,
yes,
but let me take a look at it before you post it. Is that okay?
Okay. Okay, that's fine. That's fine.
Okay, thank you so much.
All right, thank you. I believe you can start now. Hello, everyone. My name is Akinpelumi Omoni. I'm the chair of the IEEE PES Student Branch Chapter here at the University of Manchester, UK. PES stands for Power and Energy Society. We are proudly supported by the IEEE PES and the IEEE UK and Ireland section under Region 8 of the IEEE organization. Today, we'll be having a distinguished lecture program, a webinar titled The Power of Data Analytics in Electric Utilities, an Industry Perspective. Before we continue, I'd like to just share some information about about what we should know about. Please keep muted and use the chat room for posting questions. And during the question and answer session, that's after the main presentation, you are allowed to turn on your mic, and share any question or you want to comment on what has been said. Please note that the chat history will not be recorded. We're not recording any chat information you put in our chat room. But please be mindful of the information you send out. We expect that everything is within reasonable use. And the webinar presentation will be recorded and later published on our website. And please, a feedback form link will be sent to the chat room. Please make use of it and give us your feedback on our webinar. The outline for this webinar will be, I'll be discussing about, briefly discussing about our students branch chapter. I'll also be introducing our guest speaker, then we'll have the main presentation, then we'll have time for asking questions and answer, and then a brief announcement before we call it a day. So the question is, who are we? We are a student branch chapter here in the University of Manchester. We've been existing since 2012. We have a large number of student members. We've been organizing programs, events, and activities that are centered around power and energy for years now. And for our excellence, we've won a number of awards, international, regional, and national. Our mission statement is largely based on the mission statement for IEEE as a whole, which is to foster technological innovations and excellence for the benefit of humanity. We as a students branch chapter, we are more concerned about providing a platform for students to be able to learn latest developments within the power and energy space. We do that by providing frontier knowledge, organizing webinars, having field trips, and other extracurricular activities that would help the students to be able to aspire to become a technical expert in power and energy. And as you can see from the pictures, these are previous committee members who have served within this branch chapter. Now I'll be talking about, giving a short introduction about our guest speaker, Dr. Varadan. Dr. Varadan is currently the Global Director of Product Management for a portfolio of software products related to asset management at Hitachi ABB Power Grids. Some of these products include asset performance management, asset investment planning, data analytics solutions for outage management and work management. In his role at Hitachi, he provides strategic and tactical guidance in realizing a broader vision for these products in alignment with the electric industry. He has a blend of business, technical, and leadership skills combined with a keen customer focus in achieving a key goal of enabling customers to make holistic asset management decisions. Furthermore, Dr. Varadan has held various leadership roles throughout his career with OEM vendors and other consulting companies. He's a regular speaker, panelist, and instructor at IEEE conferences, and lots more. In recognition for his fantastic accomplishments, he was appointed the IEEE Distinguished Lecturer on Asset Management in May 2020. He is also a senior member of the IEEE PES group. an author of Shaping an Engineering Career Advancement to Management, and a contributing author of the book Smart Grids, Advanced Technologies and Solutions. On this note, I would humbly invite Dr. Varadan to make his presentation on the power of data analytics. Hello?
Sure, yes.
Yeah, okay. Please,
yes, very good.
you could share your slides,
so
please.
let me start by sharing my screen. So if you would unshare, then I can share.
Okay. Okay, I'll stop sharing.
Okay, do let me know if you're able to see my screen. It should be a lady running on the beach.
Yeah, we can see your screen.
Okay, perfect. And let me get started here. Okay, you should see my first slide on the screen. Well, thank you very much. I appreciate the kind invitation from the University of Manchester, Omonini. I appreciate your setting up this talk. In fact, if I remember correctly, many years ago, I used to have the same role as you when I was chapter chair for student chapter way back when I was a graduate student. And I continued that role even when I was, a working professional. I was chair of the San Francisco chapter. So I completely understand and appreciate the work that you put into organizing something like this. And the accolades that your chapter has accomplished is phenomenal, right? To get such recognition for a chapter is really nice. So that's clearly a testament to the good work that you guys have been doing. So, pat yourselves on the back, the entire AdCom committee. You guys are doing a fantastic job. Let's go ahead and get started. I want to again thank you, and let's get started with the topic, right? Yeah. So we've all talked, if you pick up the, any, advertising, any job posting, service, you will notice that one of the hottest jobs today is data analytics and machine learning. Okay, there is something that is a sort of a phenomenon that has been happening. Not only in the electric utility industry, but in other industries also. And it all starts with data, okay? So what I want to do as part of this presentation is give you a high-level understanding of the role of numbers and data in an electric utility, and focus on real-life cases, right? So we'll start off, my agenda is laid out here. We'll start off by understanding data, and we'll do a little safety moment, but at the same time, I want to show you some of the power of data visualization. This is an important part, which will come back later too. And we'll talk about, electric utilities in general. I use the word complex number there as a pun because, as you guys know, we use complex numbers as electrical engineers. But that said, we're talking about, lots of numbers. And the question is, where does this come from, right? And then the question becomes, what do you do with all of this stuff? Because numbers by themselves are meaningless, right? So you need to have the context, you need to have, the analytical ability and the business sense to know what to do with the vast data, vast amount of numbers that you have in front of you. I will take asset management as the primary use case for what we will talk about, because that's the area that I specialize in, data analytics and asset management, and take you into further details of how you would actually do an analysis, right? And I'll present some case studies of what we've done for our customers, and talk a little bit about the future of data analytics, right? Where is this thing headed, right? I mean, in terms of new tools, new techniques, and new sorts of things that we are seeing in the industry, and also what we're seeing from our perspective is people who create solutions for the electric utility personnel to use. Okay. I would love to have any questions that you might have. as we go along. Omanini, I will leave that up to you if you want to coordinate that chat, session at the end, or interspersed in through my call, through my talk here. I'm okay either way. I'll let you handle that. Okay. Okay. So let's go on. So let me start off with a simple safety message, right? I can present something like this. This is basically an Excel sheet that has, text out here that tries to describe something in terms of a worldwide pandemic that we have recently experienced, and that we've also been experiencing even now in some parts of the world. It's still a big thing. But when you put something like this in text, it doesn't make much sense at all, because for somebody who's reading this, you're going to be wondering, this doesn't make any sense at all. But if I put something like this in front of you, right, this at once brings all of that data there, all of that textual message, all of those text messages that I had there to light. So notice what we're doing. We've reorganized things. We've reorganized things in such a way that we're making use of colors. We're making use of, the font sizes. We're making use of bubbles that can be bigger or smaller based on the impact, right? In terms of the risk here. Now, when you put something like this, it doesn't take a genius to figure out that, hey, look, going out to a nightclub is probably the most high risk sort of activity when it comes to spread of COVID, right? So a picture is worth 1,000 words, right? And I put this up here to serve two purposes. One, there's data. Data can be in the form of text, right? But you can still do stuff with it. You can still visualize it. And the way to visualize it brings out the effect of all of that text in very clean, very clear and plain sight. Okay? So data analysis is something that you do on the back end, but when it is presented to the end user, there are several visualization techniques that allow you to bring that impact in a very effective manner. Okay, so keep that in mind. We'll use this later. Okay, but here, just understand the safety message and understand that data is beautiful, right? Especially when it is presented in a way that makes sense. Okay. Now, let's start thinking about data, okay? So here is something that I was looking at in an article in the Wall Street Journal a while ago. And this talked about a very interesting way of how to understand data explosion, right? Let's start with the illustrations that were there. So let's consider this, right? If 1 grain of rice, okay, 1 grain of rice is equal to 1 megabyte, right? Then one low resolution photograph, and we all take photographs, right? One low resolution photograph is 1 grain of rice, okay? So therefore 2 GB, 2 gigabytes is about 1 serving or 1/4 cup of rice. And 2 DVDs, which is about 8 gigabytes. And for those of you who remember the older days when we had DVDs for movies and things like that, now it's all streaming. But that's 2 DVDs, which is 8 GB, is about 1 cup of rice. Okay. Keep that in mind. And the reason I bring this up here is because I'm going to show you something very quickly. Now, if I consider MLB, right, which is MLB is the Major League Baseball. That's an organization that conducts a lot of baseball, something like your cricket league or your football league and so on, right? So if I'm looking at MLB has 4.7 terabytes of data, and I'm talking about annual data. So if you look at it there, that's roughly 235 pounds of rice, okay? Remember where we started from. We started from the simple 1 grain of rice. Now, on the other hand, if I take YouTube, which all of you are familiar with, YouTube produces something like about 4860 terabytes of data annually. That is the equivalent of about 122 tons of rice. Okay, so just think about how big this is, and this is just one part, right? There's YouTube, there's so many other things that are going on in the internet. So just imagine how much of data is being created on an annual basis, on a daily basis. So let me ask this question then: what about an electric utility? Right? So my estimation is that an electric utility creates roughly between 3 to 5 terabytes of data annually. And again, this depends on the size of the utility, right? A utility that is large, like an American Electric Power here in the United States, which covers 13 different states. If I look at Duke Energy, that's probably about 8 or 10 different states. And then there are smaller utilities that cover maybe just one state or maybe a part of a state, right? So if you take all of that into account, that is roughly the equivalent of about 140 to 330 pounds of rice. So that's one electric utility. Okay, let's keep that in mind and let's continue further, okay? Now, where is that data coming from? If you look at the electric utility, you have to understand where is that data coming from and what is the type of data that is coming from each of these different sources. And also you want to understand, more about how you would characterize this sort of data, right? Now, most of you are probably familiar with the 3 V's of big data. The 3 V's basically correspond to velocity, data volume, and data variety, right? They're pretty self-evident there if you look at the circular chart right there. One that talks about how quickly data is being generated, and then the other talks about how much is generated over a period of time, and then the kind of data. Now, what data sources are there in an electric utility? So let's start from generation. I mean, what I've shown you here is the conventional data flow or power flow from a generator station, one or more generator stations that are located in remote areas. And then you have, step up transmission, and you get it to a transmission level, that's typically in the order of several hundreds of kilovolts. Then you bring it to load centers in the cities, and then you step it down again so that you can distribute it at, whatever voltages, right? And different countries use different voltages, 110 here in the US, 220, elsewhere in the world, right? But there's clearly generation, transmission, and distribution, which is like, vertically integrated utility. At every single point of this flow of power from the generation to all the way to the end user, data is being produced. Let's understand exactly what that data is, right? So there's different types of data, different speeds of data, and talking about data, the data could be transactional data, right? It's like how much power is sold from one to the other. Transactional also in terms of, okay, how much power did the consumer at the end basically buy, right? Because this is important for financial settlements. There's, visual data that's happening, right? There's textual data that's happening. There's voice data that is going back and forth, right? Because the operators are typically communicating with each other to the field personnel out there. And all this is being recorded somewhere. It's all being logged. Logged simply because it may be audited at a later stage for purposes of regulatory compliance and otherwise, right? Now, what do you do with all of this data, right? So the question really is it depends. It depends. It depends on what you want to do. I have a very simple example. All of you have access to Google, right? When you type google.com on your browsers, a very simple window appears and it gives you a box in which you can basically type in anything you want. But the question is, if I give you that tool and say, here you go, you have this tool. The question is, so what are you going to do with it, right? So if you're curious about, say, the GDP of China, you're going to type GDP of China and Google will do the search to basically get you any articles or any information related to that. Now, that's because you were interested in GDP of China. But what if you're an electrical engineer and you want to know, okay, something about how does automated metering work, right? So you can type AMI infrastructure or AMI vendors or AMI, implementation or something like that, and then you will get all the results you want. But the bottom line is it depends on what you want as the user, right? The tool is available to you, but what you do with it is up to you. So that said, the key thing here then is, what do you want to do given that there are all these tools, given that there is all this data? What do you want to do with all of that data, right? So basically then you have to ask, these particular questions. This basically comes down to things like, okay, let's say you're working at the utility, or even if you don't, let's say you have a whole bunch of numbers that are presented to you. So the first question you're going to ask is, what is going on, right? What is going on? I see all of these numbers. Are these numbers telling me something? Is there an underlying problem that I can detect? Maybe the numbers are indicative of a symptom. And the symptoms could be anything, right? So for example, if I take a continuous monitoring of, say, a person's temperature, right? That's going to be a whole bunch of numbers, right? Let's say the monitoring frequency is every minute. So think about it. Every minute you have, the body temperature coming to you. Now, you need to understand then that there could be a pattern here that tells me if something is wrong with this person, right? So if the temperature there goes above 100, that should tell you something. But that means that you should know that there's the threshold. So if you go above that 100, then you know that there's a problem. Okay, so this is something that is part of the data analytics, right? So diagnosis, it's like, how do you look at numbers to diagnose what is going on? So you can tell me what is the present condition. Is the person in good health in this example or not, right? Does the person have fever or not, right? And that you can tell by looking at just the body temperature. Simple enough. So then the next question becomes, okay, if I do see that there is a problem, and if I do see that, this person has, indeed a higher body temperature than what is normal, I put normal in quotes because normal can be different for different, data sets. So you need to understand the context. So for example, if I am now, a veterinary doctor and I'm getting the temperature from a dog, then I need to know that for a dog, the body normal temperature is different than for a human, right? A body temperature of a dog is usually about 2 to 3 degrees higher than that of a human being. So if I don't know that, and I'm looking at this data here and apply, my veterinary knowledge to this, then nobody is falling sick, according to my conclusion here, right? So you see, you need to understand the data, you need to understand the context, okay? And the idea then is, okay, what do I do? So prescriptive action, okay, good. And then the question becomes, if this prescriptive action is done, what is the prognosis? So that means, let's say now I see that the body temperature is high. I tell this person to, basically put an ice pack or basically take paracetamol or something like that. Then I should know what will be the impact of taking such an action, right? So this is typical of any data analysis that you will do, no matter what, okay? Whether you apply this in an electric utility, whether you go out and apply it in a business context, whether you go out and apply it to change management, whatever context you apply to, these are basically the steps. You want to understand what is going on, what needs to be done, and what will happen if you take those actions. Okay. So this is an important aspect of understanding what to do with the data that you have. Okay. Now let's focus on from an electric utility perspective, right? let's consider this area, asset management. Okay, so what is asset management? Asset management is the holistic practice of optimizing investments in alignment with the principle called line of sight. So line of sight is very simple. Basically, it says, look, if I have an asset in the electric utility that is not doing well, then I need to make sure I spend my attention or I spend my investment dollars on that particular asset to make it healthy again. Fine. But then the question comes back, okay, what is the definition of health for that particular asset? Then there's another thing also that's important. How important is that particular asset, right? If it is not very important, then I shouldn't care too much about it. Now, I can make this sort of a discretionary action because as an asset manager, I don't have to treat all of my assets equally. I'm not a doctor here, right? Because if you're a doctor, you want to treat all your patients equally. But I'm not a doctor here. I am an asset manager. If I'm an asset manager, I have the luxury of treating different assets differently because some assets are more important than others. Think about it this way. If there's a transformer that feeds a downtown area where you have, all of the city's financial activities happening, versus if you have a transformer that is in the rural area that supplies one customer who doesn't really, care too much about having continuous electricity or not. As an asset manager, I can choose to prioritize the one that feeds the city center as a higher, importance asset than the other example, right? So then the question comes to what is the return? Return again is important because you clearly want to spend, your money where you're guaranteed that you will get something back, or where the return is going to be the most, okay? So to put it very simply, asset management is all about just making sure you're investing your money on the right assets in order to achieve the best results. And in this case, from an electric utility perspective, it's, free, uninterrupted power, reliable power at the lowest cost that you can provide it at, okay? So that is what an asset manager does. So there's a couple of different pieces to this, right? So from an asset manager's perspective, you now have all of these different areas that you need to cover, right? The chart on the right side basically talks about, each of the different kinds of things that typically happens within an electric utility. Now, what this essentially means is that the whole area of asset management then needs to talk about enterprise asset management, right? Which basically is the inventory and all of the information related to the assets from the perspective of, when it was procured, when it was commissioned, who's the vendor, what is the cost associated with purchasing something like this, what is the maintenance sort of recommendations from the vendor. So all that is part of EAM. Then once this is working in the field, the next thing you want to worry about is, okay, how is it doing in the field? Is the performance up to speed, right? Is the performance up to the mark that you're thinking about, right? If it is working all right, fine, you don't need to do anything. But if it is not, then you need to do something about it. And what do you do, and how much money do you spend, and how do you optimally allocate that amount of money is the next part, which is asset investment plan. Like, how do you plan for these different things? Because typically electric utilities have a fixed budget, right, cycle, or they have to actually then work with that budget to make sure that they're getting the most work done with that limited budget. So that is how, the idea of AIP comes in. How do you invest your money? Then there's other things. How do you manage work? There are people, there's all this work that is being generated. How do you manage that work? How do you make sure that all of that work is getting done, right? See, at the end of the day, asset management is really about two things. Identifying the right work. Okay, I put right in quotes because identifying the right work. And the next part is doing the work right, right? Again, I put right in quotes because The second part is all about work management. The first part is all about asset performance management. Now, there are other things also that we consider as part of asset management, which is field services management. How do you manage all of the people who are and the crews who are basically doing all of this work? And last but not the least, vegetation management, which is part of the overall picture, but it's a very important thing for an electric utility. In fact, that's one of the things on which electric utilities spend the most amount of money. If you consider the statistics, most faults in electric networks happen because of vegetation problems, right? Almost, they say, close to 60% of outages on the distribution side happen because of vegetation-related problems. The remaining 30 are due to asset-related problems where equipment actually fails, right? Okay, that said, let's go on. So I want to introduce the concept of a use case. Okay, so a use case essentially is something that you talk about from the perspective of a user, right? So what do you want to do as a user? So in an electric utility, let me say I create a use case for myself. I'm curious about understanding the relation between rotor vibration and the health of the rotor as a function of time. So like you do in any statistical experiment, right? The first thing you start off with is a hypothesis. And data analytics is no different. You start off with a hypothesis to say, okay, I think there is a correlation between the rotor speed and or rotor vibration and the health of that particular rotor. So this is something that is that you intuitively figure out, and then you say, okay, my hypothesis is that there is a direct relationship between the two. Now what you do is you get the data, and then you basically go through the remaining steps to understand the correlation, and then you can put together your confidence limits, right? So this is something that most of you would have been exposed to in your basic statistics classes, right? So you put a student t-distribution, ultimately understand the confidence intervals, and see how well your hypothesis worked out. Same thing here that we do. We come up with a hypothesis, and we say that is our use case, and we say that is what we want to understand. Okay. Similarly, if I look at something else on the transmission side of the business, I want to predict a failure event based on observed measurements, right? And these are observed measurements that are taken at a substation transformers terminals. So you want to look at measurements there and say, I want to know when this particular asset is going to fail. Right? So these are use cases that you can define, and there is really no limit at all. You can pretty much think about anything that you want in terms of a hypothesis, cast it in the form of a use case, and then take the next steps, which is find the data that basically needs to support your hypothesis, and then run through, basically the statistical assessments to see how well your hypothesis holds. Similarly, on the distribution side, you want to predict outage restoration time as a function of the storm severity. So if it is a category, let's say 5 storm versus a category 1 storm, how quickly, are you able to estimate, or how quickly are you able to restore power, right? That's ETR is essentially the estimated time of restoration, right? And that's something that most utilities publish as part of their customer information management. Okay, so this basically comes down to this. If we are to look at the asset management use cases, right, especially from asset performance management, what are we talking about here? So I've split this up into 4 different use case profiles. So we have basically the asset manager, then there's the financial manager, there's the planner, and then there's basically the person who's the field worker. So in here, these are some of the use cases, right? as a manager, I want to know what is the condition of my asset, what is the associated risk of failure. Now, why do you want to do this? You want to do this because, remember, from an asset manager's perspective, if you work for a utility, your primary goal is to make sure that you're giving your customer uninterrupted power, highly reliable power, uninterrupted, at the lowest cost possible. Okay, so those are the three things that you're really thinking about: the reliability, the availability for the customer's perspective, right? How do you do that is by asking these questions, right? So then the next question you would ask is, why is the asset in a particular state? And again, all of this is supported by data. Okay, so the question then becomes, what data do you get to support these questions? What data should you to get, right? What frequency should you get it at in order to be able to answer these questions, right? And then last but not the least, we'll then talk about what are the techniques associated with, all of the stuff. Like, what do you do with that data in order to be able to get you to that nice, colorful picture that I showed you earlier, right? So these are some of the questions that are very typical for each of these user profiles, right? Ultimately, where is this taking you? Ultimately, this is taking you to the question of, should I repair or should I replace a particular asset, right? Think about it. If you have a car and you drive a car and your car is, in a particular state that it is, okay, you can do visual inspections to, for example, look at the tires and say, okay, the tires don't have enough tread on it. So now you naturally ask yourself the question, hey, can I push this a little more? Or should I, run it to failure? That is one way you can do it. If you run it to failure, you're at your own risk, because, if your tire blows up on a highway or a freeway, then you're in big trouble, and you don't want that. So the next question is, okay, can I just fix it up temporarily so that, it continues to work for maybe another year? Because, after a year, I'll graduate and I'll have enough money to buy myself a new car. Okay, so that is the question of repair. Can you do some repair at this point of time so that you can avoid or defer, a capital investment? And then again, the last but not the least is, okay, there's nothing you can do, you have to replace it. And then the question becomes, if you have to replace it, are you going to replace it with a like for like, or are you going to introduce it with a better tire, right? That's, but then you're going to ask the question, there's no point, putting something really nice on this car, because the car itself is not worth it, right? So these are all the decisions that a typical asset manager does, right? I use the example of a car, I use the example of the tires on your car, but this is exactly what an asset manager does. We're talking about big, large transformers. These big, large transformers cost several, tens of millions of dollars to replace. But there are parts on it, like, for example, bushings, or, for example, the tap changers, or the oil inside of the transformer, right? These are all things that can be changed. Those are all things that can be maintained, and each of them has a different cost. So the question then becomes, okay, how do I manage this whole thing so that I minimize, the overall cost of, operation for this transformer, right? So these are what typically the kinds of questions that keep most of the asset managers, planners, and the financial people, up at night, right? The people in the field are always thinking about, how do I know where the bad actor is? When I say bad actor, in this case, it's the asset that is going to blow up, right? Where is that? How do I get there? How do I get there is easy, right? Once you identify where it is. Then the question is, when I get there, what do I expect? I mean, is it going to be something catastrophic, in the sense that, I need to make sure that I'm protected, so there's a safety component there. And then there's the other thing, which is, once I get there, what do I need to do? Do I have the parts? Do I have the skills? And does the screw have all of the requirements, certifications, and so on in order to be able to perform this work, right? So these are all the kinds of things that happen in an electric utility. Now, all of this is powered by data. Okay. Now, I'm sort of putting this in a casting this in a different light. The reason is because I want you to understand what you should do with that data. There's tons of data, as we saw before, but the question now becomes, what will we pick and choose from the data that's out there in order to answer specific questions? And in order to do that, you must have an idea of what questions you want to answer, right? So you have to, the whole intelligence in data analytics is in how you cast that question, right? You cast the question in the right way, then the answers become obvious, right? Because the next question after that will be, okay, I've cast this question. Now what do I need to do to answer this question? Then you will say, okay, let's put a sensor here. Let's put a monitor here. Let's get this data back. Let's measure it over a period of time. Let's do some statistical analysis on this data to see what is normal and what is not normal. And then, you get to the point where you're able to say, okay, if this and this and this happens, then I think I have a problem. And so therefore, my hypothesis is, proven to be right or wrong, right? So this is what we typically do as asset managers. Now, you can apply this for a generator. You can apply this for an SVC component. You can apply this for transmission, the whole transmission system. You can apply this to a distribution, asset. You can apply this to pretty much, anything that happens to within an electric utility, right? So that's, what the importance of asking the right questions is. Okay. Don't get bogged down by the data right now, but ask the right questions and the data will automatically, help you get there. Okay, so let me drive this point, even further. We've talked about the electric utility, like if you think of that as the universe. Now we're down to the substation, and in that substation we're talking about one small unit called the transformer. Now the transformer, as it happens, is one of the most important things in a substation. Why? Because it is one of the most expensive assets to replace, right? And remember, I told you in the beginning, as an asset manager, I have the luxury of picking and choosing which assets that I want to work on. And how I do that is based on the importance of that asset. And a very simple question to ask there is, if that asset fails, what is the impact, right? Then immediately things become clear. Oh, okay, if this transformer fails, downtown financial, operations are all stopped. So guess what? This is a very important transformer to work on. So the question there becomes, what happens if it fails? Now, if you're able to answer that question and if you're able to quantify that, then you have an immediate understanding of how important that particular asset is. Okay. So now let's take a particular transformer and now let's get into the deep details of this. Okay. I want to walk you through this process so that you understand that, there is a lot that you can do with the data, but you have to go about it in a methodical manner. Otherwise, you're not going to end up with anything useful for you to be able to, take an action of it. So if I'm talking about a transformer, let's talk about nameplate information, right? You guys are all familiar with nameplate information, which is, what is the kilovolt, what is the kV, what is the, primary, secondary, all of that, information. The next question is, what are the failure modes? Now, I don't know if you guys know about failure modes. We'll talk about that in just a little bit. Failure mode basically means, how does the transformer basically die? Okay. If I take the example of a human being, human beings have many, many failure modes. You can die of a heart attack. You can die of a, liver, failure. You can die of kidney failure, right? So these are all failure modes. Okay. Now you can classify them further, but for our purposes, that's good enough. For a transformer, failure modes would typically happen and I have a chart later to explain in specific ways, right? For example, the tap controller might fail, right? Or for example, the chemical content in the oil there might rise very high, and that could lead to a failure mode, which basically the dielectric constant there breaks down, and so now you have conduction instead of insulation being provided in the transformer. So you have to understand those failure modes. Now the question becomes, okay, if you understand the failure modes, do you know what parameters can be measured that are indicative of those failure modes, right? So for example, in this case, if I know that overheating is a problem, right, then obviously what I'm going to measure is I'm going to measure the temperature, right? If I know that the gas composition is a problem, then what would I do? I'd basically put in a sensor that monitors the level of the dissolved gases, right? For example, acetylene, or and so on. So you must know what is going on, and you must know what are the parameters that basically describe that failure. Now, and the question then becomes, are you getting all of these at the right frequency and the right granularity, right? Because sometimes some events are quick, sometimes some events are slow. So for example, partial discharge is one of the things that we typically measure on large high voltage transformers. Those are fairly quick events, especially once you start detecting that there's a problem, right? Within 8 to 16 hours, within 8 to 24 hours, there will be a failure, and that failure will happen. But there are other parameters, for example, DGA, which is relatively slower, So when you see changes in the dissolved gas in a transformer, that's indicative of a failure coming, but it's not in the next 8 or 16 or 24 hours. It's something even further out, which is probably maybe 2 years, 3 years, 4 years, right? But nonetheless, you have to know that these are the kinds of things, these are the characteristics of these particular parameters. So you know what to do with it, right? So that's where you come down to, have you established the thresholds associated with each one of these, right? How do you know what is normal? How do you know what is not normal? Then, do you have anecdotal information related to this particular unit, right? And this comes from the field experience of people who've been out there to inspect this particular asset. And last but not the least, once you've got all of this information, right, how do you put all of this together into something that gives me a probability of failure? And you want to do this for not just one transformer, you want to do it for all of the transformers in your fleet, right? And how do you basically come up with a probability of failure, so that now from a mathematical perspective, I can look at this list of transformers and then say, okay, this is a failure of transformers much higher than this one. So I need to focus on the one that has the higher probability of failure if I'm going to make any actions, right? Okay, let's go on next. Let's look at how we continue with this transformer example. Now, I put this example here of the 5 blind men. I'm sure all of you guys are very familiar with this. This comes from probably, stories that you may have read, or maybe your parents told you this when you were growing up, right? 5 blind men looking at an elephant, right? And each person basically has one observation here, So if you're looking at this from a statistical perspective, each one has one observation. You cannot make a determination by just one observation, right? And that's one of the fundamental principles in statistics. You want a sample, and the sample size should be big enough so that at the end of the day, the conclusions that you make are corresponding to the whole big picture, right? So the idea here is, if I'm looking at a transformer, let's say this, in this case, my elephant is a transformer, I can get partial discharge patterns. I can get dissolved gas analysis patterns. I can get standard oil tests. These are all like single views, right? Of looking at one aspect. It's like, the blind man number 1, blind man number 2. Each of them is looking at one aspect of the transformer, in this case, the elephant. So now the question becomes, how do you put it all together? Because at the end of the day, when I take all of these things here, partial discharge, dissolved gas, standard oil, electrical data, visual data, and all that, I want to build the overall picture of the transformer. I want to build that overall picture that basically says, okay, I have an overall health of this particular transformer. So the key thing here is knowing how to put all of that information together, right? Synergizing all of that data, right, into a larger picture so that you're able to get the total picture. Now, key things here. At the end of the day, it really comes down to, making sure that you're able to understand these patterns, right? And when I say patterns, these are patterns that are typically what somebody in the field, over a period of time would have experienced and understood, right? To basically say, okay, look, if, you have a lot of water in the oil, for example, and you see that, the temperature, is rising inside the transformer, and you see that something else is happening. So these are typical patterns, right? Now, when you know that these three different things are happening at the same time, it's very likely that the transformer is going to fail in a particular way. So this sort of information is really what we call the subject matter expertise, right? The subject matter expert, who's built this over a period of time, would basically be somebody who can help in terms of being able to help you with this objective of determining the health of this transformer. Now, pure data science without the subject matter expertise is useless, okay? And I tell you this from my own experience. The context is key. You must understand the context, and you must be able to, understand, the engineering aspects of it, the data science aspects of it, combine the two together in order to be able to do what you do next. So for a lot of the folks, on here on this call, presumably students, if you're thinking about, data analytics as being your main area, or electrical engineering as being your main area, remember, at the end of the day, data engineering, data analysis, and all that is just the toolkit, right? You can either specialize in the toolkit, but then at the end of the day, you really don't know anything, because if you don't know how to apply it to the electrical side of, the asset, you really cannot make the two meet. And at the end of the day, the two have to meet together in order for you to be able to, get the value out of what you do, right? So think about it this way, right? If you're a mathematician and all you've done is specialized in calculus, okay, you know calculus very well, but if you don't have an application, then that knowledge is really no good, right? So remember that putting the two together is really what will make you successful, right? So learn the tools by all means, but also make sure you learn the electrical side of the business, right? So then what will make it very effective for you is to put the two together. And then you're able to make, decisions, you're able to make judgments about what you need to do. All right, so getting down into details, right? So this is now coming at it from the side of the electrical side. If you have a look at a transformer, these are all the things that are in here. I don't want to make this very complicated, but it is as complicated as it is here, right? There are active parts, bushing, cooling. Each one of these has, separate, things under it. You take all of this and you basically then say, okay, based on all of these are the different kinds of parameters that I would need to measure. And these parameters are indicative of these failure modes, right? So if I build it up, then I can take all of this and basically say, okay, there's a short circuit probability of failure, there's a dielectric probability of failure, high temperature probability of failure, accessory and miscellaneous. I combine all of this to get me the probability of failure. I combine that with the unit of importance, which is essentially how important is this transformer, and then I get an idea of the risk of failure. Okay, so this is the typical steps that you would go through in order to establish the risk of failure of a transformer unit, right? So things to remember: you cannot do this unless you understand what a transformer is. You cannot do this unless you understand how a transformer fails. You cannot do this unless you understand how the parameters that are descriptive of these failure modes are measured, right? So you need to get down to that level of detail to be able to understand how to apply then the data analytics tools that you now have mastery of to the data set that you're getting here. And then you make sense of it, just like how, you put all of the blind men together to come up with the overall picture, right? So that is the key. Now, let me show you some of the typical things that are available in the industry today, right? So here's an example of one of the solutions that I've been, involved in the building of. This is measurements that you're seeing from DGA, dissolved gas analysis, for a particular transformer unit. You see up here, we've characterized it as red risk. But how did we come to that red risk is based on all of these different graphs here that you see, right? And this is just one piece of it. These conditions down here, the IEEE standards that basically determine the thresholds for each of these different layers here. You see there's green, yellow, red, right? So those are the different thresholds. So then the question becomes here, if you look at the tab here, there's DGA, dual, Rogers ratio. These are all different things that you can do, right? Different sets of data. In fact, in this example, there are more than 500 parameters that are being monitored. 500, okay? In order to come up with that risk assessment of red. This now is the next question, which is now you have all of the data. What do you do with that data? So there is something called a dual analysis. And again, this is a published work. This essentially talks about, the different states in which a transformer can be. Now here, what you can do is you can see, okay, now all of that data means something. So for example, if this dot is at, some point here in this shaded zone, then I can look down here and basically say, okay, I expect that, thermal faults are going to be more probable. Or for example, if I look at type 4, I can see that, okay, in that particular zone, if my dot appears there, then there's a particular, higher probability of, a stray gassing event, for example, right? So this is what you start doing. You get that data, you process it in the background, and then you have specific tools that are specific to the kind of, analysis that you're doing here in order to come up with these conclusions. Now, what does this do for me? What does this do for me at the end of the day? Remember, I should be able to calculate the risk, and that's what I see here, risk, in these different zones, and there's importance, condition, and here is history of, what brought me to this current state of this risk being red. These are all the different probabilities here that then I'm now, I've computed. So this is the sort of analysis that typically is done. Now, remember, here we're talking of one transformer. In an electric utility, you will have thousands. In fact, the largest deployment that I've been involved in was with a company called American Electric Power. We have something like about 8,600 transformers, okay? Now think about it. If you are the asset manager and you think that doing this for one transformer is difficult, that's where the beauty of software comes in, right? I can do this for 10,000 assets without any problem because I can then visualize all of them using the power of data analytics, okay? So that's what I will get you into. And the next step that I want to do is I want to walk you through a case study, okay? So this case study comes from a customer that I've been working with for the last 7-8 years now. A company called American Electric Power. They're a large company in the United States. And then there's another one that we've also worked with. This is a generation example, and I'll show you both examples and show you how everything that we've talked about is being applied, okay? So here is this case study, American Electric Power, large, I think one of the largest owners of transmission in the United States. They cover something like about 4 RTOs. RTOs, regional transmission operators. And as you can tell, they span all the way from the Northeast all the way to the West, Midwest, this is Texas. covering about 13 different states, and they've been in business for over 100 years, right? So what was their, business use case? Their business use case was very simple. Many years ago, one of their vice presidents made a comment and said, my wife's little Honda Civic is much more advanced than this large power system that I have. And he said, it's because I can monitor everything, or my wife can monitor everything that's happening to her car on the dashboard. But I have $1 billion power system here and I cannot do that. So that statement basically got us working on this project. And they also had a paradigm. They wanted to make a paradigm shift, which was, they wanted to move away from the time-based maintenance, periodic maintenance as it is known in the industry, and also run to failure sort of maintenance, to a more condition-based renewal and maintenance, right? And so the Asset Health Center was the project that it started out as, and I was very fortunate to work with them ever since it started, right? So this is a large data analytics project that is implemented. It's been in production since 2015, so for now almost seven years, and the results are very, very encouraging and have been included into all of the business aspects of the electric utility, right? So this is what they do. They basically get operational sensor data, inspection equipment data, run it through this Asset Health Center. That's the software, and that's the data analytics that we built for them. And they're able to come up with something like this, right? So you see now the power of the data analytics. Remember, we are considering more than 8,600 transformers, right? And that are spread across the entire United States, right? From Northeast all the way to Texas. And at the end of the day, we come up with something as simple as this. We say, look, in this area here, this is of course a clustering that is happening here. So we're basically saying there are so many substations here. And of these substations in this geographic region, so many are red color, so many are yellow color, so many are green. So at once, this is an extremely powerful visualization, because if I'm looking at this from an asset manager's perspective, I know exactly where I'm having problems. I immediately begin to think about the next things, which is, I have a health score. I then need to start thinking about, how would I maintain these assets here? How would I basically consider replacements? And, if I'm a field worker and I'm out here on my little PDA or, iPhone, I can essentially look at all of these results to know everything that I need to know before I enter a substation, so that if there is any activity that might lead to a catastrophic failure, where my life as a field worker is going to be in jeopardy, I want to know that ahead of time so that I can take precautions. Either I avoid going there, or I tell the operators to give me an outage before I go in there, right? So there's a huge safety related aspect to this. These are some of the dashboards, right? And as you can see, the visualization here is all in terms of red, yellow, green assets. We're basically putting all of the assets, and then there's many different ways in terms of displaying this data, right? You can display it by age, you can display it by voltage class, you can display it by type of voltage, you can display it by geographical region. There's any number of ways in which you can, they call it splice and dice, right? The data, right? Then the other part also is the trending. Trending is an extremely important part, because in a lot of cases, remember I talked earlier about baselines, right, for temperatures. In some cases, different assets, even if they're made of by the same vendor, might have different baselines. The reason is because of the way that they're operated, or because of the way that where they're located, right? So for example, same transformer made by the same vendor, one that's in a colder climate versus one that's in a warmer climate, they behave differently. They have different life characteristics, right? Simply because of the the conditions that they're exposed to. So the other important thing, is from this case study was, understanding failures and understanding failures before they happen, right? And that's key, because if you look at this transformer on the right side here, that doesn't look like a happy transformer. It's been fried, right? It's literally been fried because of a catastrophic event that happened. And that's a huge transformer. If you can see, the comparative size there of a person right next to it, it's almost as big as a house, right? So when something like this fails, you don't want to be close to it. But what you want to know is you want to know when it is going to fail, right? So that you can take corrective action, right? So one of the things that this data analytics was able to do was to be able to monitor, this action. And what we were also able to do is, while it failed, since we recorded all of the data during its failure, we're able to use that as our prototype for, thresholds that we want to look at for other failures, right? So you learn from, your observations, and that is what you do in statistics, right, and data analytics. The other example was, a transformer that failed, again, a 765 kV transformer. In this case, because we had learned from the first one, we were able to apply those thresholds, and application of those thresholds basically helped in terms of being able to turn this transformer off before it failed. So there was another example of, a situation where the transformer started gassing, very unusually. Hydrogen and acetylene levels rose very quickly. Partial discharge was seen in conjunction, and transformers again taken out of service. Now, this is again very important, because when these transformers fail, they lead to a lot of consequences. The most obvious one is no power. But there are lots of other things that happen also, right? Safety aspects. If it fails disastrously, catastrophically, it could lead to a lot of problems. The other thing is, from a planning perspective, always, if you know that something is going to happen, you can plan for it. Planned work is always cheaper than unplanned work. When you have an emergency, you always have a bigger problem, right? Because now you're scrambling for resources, you don't have people, in the right places, and you don't have the spares in order to be able to, make a replacement or take corrective action, right? So the big benefit here was in terms of being able to catch transformers, catch failures before they actually happened, right? There was, of course, the improved safety for field workers, to make sure that they can go in without any problems. And the involvement with planning now, is in a much better state, because they know what to plan for. Not only from the perspective of building new assets, also from the perspective of knowing what to replace, when to replace, and also in terms of managing work, right? These are all very important aspects. The other key thing is, if you understand, from the economics of how a utility works, utilities typically, make money on the capital that they deploy. Okay, so it's very important to understand this, and this is most typical in all regulatory regimes, right? So the more capital they deploy, the more money they will make. But the electric regulator, the utility regulator, does not allow them to deploy capital, in huge amounts, because, unless it is necessary. Now, what having a monitoring system like this has basically helped, this company with, is to be able to make that case for, capital equipment, right? So that's a really big advantage, of having something like this from the utilities perspective. Okay, good. Let me talk about another example. This was a customer from Europe. Give me just a second, please. This is another example from Europe. We're talking about a generation plant here. And as you know, generation is a very important part of this whole equation, right? Because there is a lot of money in generation, right? So every megawatt hour that is sold, is basically money in the pockets of the generators. But there are some key things that happen here. If the unit fails, that also means that that's money that is not coming into the pocket of the generator. So what do you think is the generator's interest? The person who owns the generator wants to know what is the condition of my unit, when will it fail, right? When is it going to fail? And the reason of when will it fail is going to be important, because then the owner can plan for that loss of revenue, or maybe include something else in the portfolio to make up for that loss of revenue, or necessarily take corrective actions, right? So this is important, and especially in the generation perspective, because market prices are set. Well, I said prices are set by the market, right? So depending upon high load, low load, and things like that. So from a generator's perspective, it becomes extremely important to know, what the future condition is going to be, right? So if you remember the previous use case, when we talked about American Electric, that was more about what is it now, what is wrong with the system now, what corrective actions can I take? Here, this goes one step further. It says, what will happen to this particular unit? When will it fail, right? So we're talking about the prognostics, right? So if you remember in the beginning, we talked about the typical use cases, what do you do with data, right? One is diagnosis. The other is prescriptive assessment based on your diagnosis. Then there's prognostics, which is future, what is going to happen in the future, and that's essentially the forecasting capabilities, right? So you use the data to basically forecast what's going to happen. Why? And you can see, if you know what the future is going to look like, you can plan for it, and you can, make money off of that situation, right? Think about it. This is very much like the stock market. If you knew what the stock market would be doing tomorrow, you would plan for it accordingly, right? Same thing here. If you know what the generating unit is going to do tomorrow, 3 months from now, 6 months from now, you can plan for your actions so that you optimize on, your actions so that you can maximize your profits, right? So that was the use case here. The plant had a lot of data, right? And this is very typical. When you go to an electric utility, you will find lots of data. What is also very typical is that data is in different silos, right? Also, what is very typical is that these silos don't talk to each other, right? Because there is no underlying, mechanism that ties all of this together. So you might ask the question, why is this situation like this? The reason is because, when an electric utility historically started operating, right, each had their own specific function. So for example, operations had a specific function, planning had a specific function. So they collected the data that was necessary for them and used the tools that were relevant to them. But the problem is we're talking about the same assets now, right? So it's like, the same elephant, but now different blind men looking at it. So that is where now, the power of data analytics is to put all of this together to come up with the overall view, right? So that is what we're doing here. So what is typical in an electric utility also is you will find data in multiple formats, multiple frequencies, different granularities. The idea is, how do you put all of this together, and how do you communicate the information that you get, right, in terms of commitments for the generating units here, so that you're able to maximize the financial gain, right? Okay, this is a little bit more about the customer. Let me show you the actual solution that we came up with. So this is an example of the the units. Units were in Europe, right? So let me show you the. So here are different failure modes, and this is an example of, when we think the units there will basically go from green condition to red condition. So you see, we're basically doing a forecasting, right? So we're saying in September it's green for this particular unit. As you start getting towards the end, towards October, things are starting to become yellow, and then as you slowly get further into October, November, you start getting into red condition. Okay, so this forecasting capability is essentially what was useful, and in this case we're talking about not only understanding when the unit will fail, but also how the unit will fail, because we're talking about the different malfunctions, right? And so you see here, as you go further out, as you get further out, in terms of a year, 2 years away, things are not very clear, and that's why it's hazy out there. But we nevertheless come up with some sort of computation. Now, what is running behind here in the background is a lot of data analytics techniques, mathematical techniques, from Markov processes to Bayesian processes, right? And a lot of statistical processes in the background, right? So remember, you must know the tools of the trade, and doing courses in data analytics, especially statistics, mathematics based courses, will help you in understanding what you need to do with all of this data, right? So those are the tools, and then you have the software and the computer side of it, which is essentially learning Python or learning MATLAB, and these are the different sorts of things that you can use, and then getting used to other large things like Hadoop, and so these are all, again, technologies that enable you to do stuff. But it ultimately comes down to, do you understand the business? Do you understand the use case? And then, how do you marry the two together? Okay. So here is another example. The same thing. We're now talking about the different components within, the asset here itself. Looking at the failure modes again. When each of these failure modes will turn from green to to yellow to red. Okay. Same thing here. We also characterize it by different probability of failures in each case. The reason this is all very useful, again, is you're able to predict when the unit will go bad, so that you can plan for an outage. And planning for outages and planning for scheduled work leads to a situation where you optimize your cash flows, where you optimize your finances, right? Emergency work is a no-no. You don't want to have emergency work, okay? And any one of you who's ever been to an emergency room will attest to this. When you go to the emergency room, you pay 10 times more than if you go to a doctor during regular hours, right? So same idea here. If you get into an emergency situation, then you end up paying a lot of money to fix things, right? So you want to plan for any work that you have. All right, so let's talk about the future of data analytics, right? So far, the kinds of things that I've been involved in, are very, related to the assets. But there are other things that we're also seeing now in terms of data inputs, right? So the typical inputs that we had in the past were things like, numerical values like partial discharge or, gas measurements or whatever, right? There were also, visual inspections that were done, but they were a little different in the sense that, an operator actually looked at it and then came up with an assessment. But where things are going now, next steps, are in terms of using visual data analytics. So here in this example, we're talking about, intrusion, right? So a person getting close to a substation. Okay, so this is substation intrusion. That's one big use case. And this is happening automatically. So there's basically a camera there, and the camera is, is detecting, any movements around the fence, right? Why is this useful? Again, it's useful because you want to protect your asset, which is the substation in this case, right? From unauthorized entry. This is also the same technology is being used in automated, for example, automated inspections. Many of you may have seen, the dog. It's called Spot the Dog, right? And SPOT is the name of the dog, and this is a robot that has been created by Boston Dynamics. So at this recent IEEE T&D show that I was, 3 weeks back, Spot the dog was on the exhibit floor, and Spot had a infrared camera sitting on his shoulders. And what that basically shows you is infrared imaging, right? So you can send the dog, in a substation. The dog can basically turn in different ways, look at different assets, and come up with infrared imaging, and you can look at that infrared image and do things with it, right? For example, you can see if there's a particular phase that is running hot. If that phase is running hot, then you can send people out there to fix it. It's probably a loose connection or something like that, or you might be having other issues, right? But it all comes down to this: the data is data at the end of the day, whether it's visual data, whether it is text data, whether it is anecdotal data, whether it is acoustic data, right? It's data, it's numbers. It comes down to zeros and ones. What you do with that data is important, right? How do you process that data and the conclusions you come up with? So the key things that we are seeing in the future, and at the upcoming DistribuTech conference, which is next week, there will be lots of new things that vendors will basically be showing to potential customers, right? Visual analytics is one of those things that is going to be a big thing, and that includes vegetation management using satellite imagery also, right? So this is another key part, which is basically you've heard about the situation where you can fly drones over transmission lines to be able to do assessments. But now think about it: when a drone flies over a particular transmission line, it can be taking thousands of pictures, right? Now you have thousands of pictures. What do you do with all of these pictures, right? Clearly, it's going to be very difficult for an operator to look at each one of these pictures and say, okay, this is good, this is not good, this is good. You're going to be spending a lot of time. So automating that with AI and ML, right? That is one of the big use cases in the electric utility business today, right? So automatically you're able to detect, right? So for in this case, you can see some of these examples here. Automatically you're able to detect an insulator, and you're able to detect an insulator versus a bad insulator, right? A good insulator versus a contaminated insulator, or for example, a pole that is in good health versus a pole that is not in good health, a damper which is bent, or a damper that is rusted out, or if you have a bird's nest inside on a transmission structure, right? So these are all the kinds of new use cases that the industry is working on, and is making great success. Okay, so again, last but not the least, this was again one of the projects that I was involved in integrating infrared images into asset condition performance, right? And here, what we're essentially doing is again, this is something you can mount the camera on a robotic, on a robot, and that was the example I was talking about, Spot the dog, to look at different images, and then come back and you can make again using AI and ML sort of techniques to make your inferences, right? So let me summarize. I know we're coming up on about close to an hour and 15 minutes of my lecture here. I want to leave at least 15 minutes for question and answers. Everything boils down to data analytics, right? It's how you use that, how you use the data. Numbers are there everywhere, but they don't tell you the whole story, right? So you need to understand the context. You need to be able to understand how to put it all together to give you that full, holistic picture. And one word of advice to you students is definitely, when you're in school, focus on developing a holistic set of skills, right? Engineering, mathematics, statistics, physics, all of these are very important because, if you're looking at the future is where, a lot of these things come together. And especially data analytics, when you talk about data analytics, if you don't know the business and if you just know, one or two tools, then it becomes very difficult for you to build that overall picture. And if you're not able to build that overall picture, then you're not able to contribute to the business, right? So focus on trying to get that overall, sort of assessment. The tools are out there. There are tons of tools to do data analytics, right? And thanks to all of the great advances in, computer science and, other fields, right? Like pattern recognition and AI and things like that. But all of those can be used in the electric utility space. Again, you have to know what to do, in the sense, like, like I mentioned there, it's about the question, with Alice in Wonderland, right? You must know what you want to do. If you don't know what you want to do, then it doesn't matter what tools you know, right? So it really comes down to that, right? There are several case studies, to show how data analytics are used in electric utilities, on generation, transmission, distribution, and a lot of the newer ones, for example, deployment of electric vehicles, deployment of chargers, like how many chargers should you deploy in a particular area, right? If I ask you a question like that, the first question you're going to ask me back is, what does my, growth look like, right? Good. So that is how, data analytics should evolve, right? You should start with the business case, with the use case, and then break it down into smaller and smaller and smaller and smaller pieces until you get to the stage where you're able to identify, specific parameters that you can then start monitoring, that then give you the means to build that big picture. Okay. So the possibilities are endless. It's like, you have Google at your fingertips. What can you do, right? And this is exactly like that. You have all of the data analytics tools at your fingertips. What do you want to do? And that is driven by, your understanding of the engineering and the business. Okay. I'll stop here and open it up for any questions that you guys might have.
Yeah, thank you, Dr. Varadan. That was very, very apt. We were educated by the fact that data analytics is highly, highly useful. I mean, not just in the present time, but in future for electric utilities. So it's time for questions and answers. If you have questions or you want to comment on his presentation, you could just unmute right now and you could speak. Or if you want to send your message via the chat room, that'd be nice. Okay, just looking at some of the information in chat room. Dr. Varadan, is it possible for us to get the slides on this presentation?
Yes, I can certainly make them available to you.
Okay. If I believe that Aram has posted websites. If you can go to our websites, Aram, can you give us information about our email accounts? So you could just send us a mail, then we'll send you the slides. I think that would be very good. So if you want to go through the slides again, just send us an email through our email address, then we'll reply you. Okay. Yeah, just looking at this. Okay. Yeah, Gomez, you can speak now. You're raising your hand. I believe it's a question.
Thank you very much.
Okay.
Mr. Varadan, you make me wonder the beginning of my career when I worked with Cerrejón, an ExxonMobil company that's located in the north region of Latin America, in Colombia. Mm-hmm. We are trying to manage the assets, the electrical assets that we have in the field, in the mine pit, and we try to manage the transformers because we have failures like that, but also the different parts of the network. The technology 10 years ago, it was not perfect. It was very complex to correlate the different paths to make that work together. But I know that you have made a very great work. The things that you show us are amazing. I love your work.
Oh, thank you so much. It's not just my work. I'm just but one, in a team. I have a team of people that work with me. A lot of researchers, a lot of software developers, who've put all of this together. So my team is close to about 80 people. Right? So it's not just me. I'm just the face of it, but there are a lot of people behind the scenes who are doing a lot of the work. So yeah, thank you. I will convey your message to them.
Yeah, thank you, Gomez. Any further question or questions? Okay. Thank you, Dr. Varadan. I think I have a question here or two, but because of our time, we've actually gone past the time. Or we'll be rounding up in the next 5 minutes, basically. Okay, Jonathan has a question. Jonathan, you could speak now.
Okay, thank you so much. It was an interesting section. It was quite an interesting session. I'm also happy seeing my countrymen in Manchester. It was an exciting session, and I can't wait to have to join you guys when you guys have the next session. It was interesting. Thank you so much. I'm from Nigeria, by the way.
Excellent. Thank you for participating.
Thank you, Jonathan. Thank you. Yeah, you can connect with Dr. Varadan on LinkedIn, I believe. Right? Or
yeah,
is there
or you have my email address, and I can send it to you, Omoni, so you can forward it to all the attendees. Okay,
Wenju, can you please get Dr. Varadan's email address? Then you put it on chat so we could all have it. I mean, that would be very good. Yeah. So I have a question here. You talked about the fact that we need to understand the toolkits, that's data analytics on one hand, and also understand the application or the technical side of things, majorly the electrical engineering aspects. And you also talked about the fact that this would evolve in the future to encompass talking about computer visioning and the fact that we would need imagery to be able to understand fault analysis, forecast, and prediction, right? And what other aspects do you see this data analytics, especially in the electrical industry, going to evolve in the next 10 years? Because I believe there will be a lot of data, because there's going to be a lot of smart grid technologies within the industry. So what does this portend as a challenge or opportunity for the future?
Yeah, so there are lots of opportunities, right? Now think about the where we are currently, right? I think the biggest problems that or biggest challenges, I would say, or biggest opportunities that we face as an industry, one is in terms of climate, right? And the other is in terms of, the global electric vehicle usage, right? So those are two of the big ones. And they're related. They're related to each other. The reason is, so those are two. I'll talk about how they're all related and so on. Then the other one also is, other initiatives related to smart cities, right? And again, let's talk about each one now. When we talk about climate change, that is huge. And the only way you can understand, climate change and its impacts is by looking at the numbers, looking at crunching these numbers to understand exactly how things have changed, how temperatures have risen, how they can be correlated to activities we've done. That ties in with electric vehicle growth, right? Because if you think about it, I see more and more electric vehicles on the road today than I did 1 year ago. Okay, and I'm only thinking, with these electric vehicles now starting to grow at such a fast rate, what that means is that the distribution network is going to be overloaded very soon. Now, the solution is, okay, you build bigger lines, you build bigger generating stations and you basically supply this load. But that is the way that is done in the past. You don't want to fall into that same trap, because if you do that, then you haven't learned really anything, right? So where things can happen now is demand side management becomes huge, right? So you can, with the existing infrastructure, do a better job managing all of this load, at the same time basically making sure that the load is met. Now, to do that, you need a tremendous amount of data analytics capabilities, right? So I see that being a really big challenge and a really big opportunity where data analytics can shine. So you still have the same sort of lines. The conductors haven't become bigger. They're still the same conductors as they are now, but you're able to schedule all of the different loads in a better way, so that you don't have to undergo a huge capital expense. So I think that's one of the big places where I see data analytics coming into play, right? Now, again, remember, from a solution perspective, on the other side, when I talk about global challenge, you do have to produce a lot more electricity as you did from before, but those electric resources cannot be coal resources anymore, because then you haven't really met the objectives. So other technologies like nuclear technologies, wind, solar, these are the big ones that people are thinking about. Wind and solar are pretty big, in the US, also in Europe and China. But there's also another part that goes with it, which is small modular nuclear reactors. These are again a newer technology, and a lot of countries, including the UK, is spending a lot of money in trying to popularize this, because you can now build small nuclear modular units that you can it's like a plug and play sort of thing, right? And they can give you up to 300 to 400 megawatts at a bank. So that's becoming also popular technology right now. So those two play with each other. Then there's smart cities. Like, think about this: when you're driving on a street, the electric lights need to be coordinated with your speed, right? If there's an accident somewhere down the road, you want to make sure that automatically, now things are rerouted, right? If there's a disaster that happens, if there's electric power that is lost somewhere, you want to be able to make sure that you divert traffic in another way, right? So these are all the things that now start coming together, because now if you think of it, everything is an IoT device, right? Everything is an IoT device that is smart. So in the past, the street light was dumb. It just turned red, yellow, or green. But now it is smart. It allows some central, dispatcher somewhere to know what its status is. So based on something else that happened, now it can change the flow of traffic. You can manage things. So these are all, some of the new concepts that people are talking about in terms of smart cities and so on, right? But the key requirement or the key component here will all be, again, now you have tons of data. What do you do with that data, right? So it again comes back to the same question, right? Data analytics is data analytics. What do you do with the data is important, and that depends on the use case that you come up with. Okay.
Thank you. You talked about IoT, and I know that in the future we would probably, or most likely, witness a high rate of cyber attacks. I mean, there are going to be a lot of cyber devices being connected to the grid equipment and assets. So what do you think about that? Then, in addition to that, there's another question here. What is the difference between asset management and reliability?
Okay, sure. So let me, that's two questions: asset management versus reliability. And the other one was
cyber attacks.
Cyber attacks. Okay, so let's address them in the same order, right? So, you're absolutely right. Because now everything is soon, taking the path where it becomes an IoT device. The cyber attack, or cyber attack vulnerability is higher, right? Because, a creative hacker can get in through any one of these devices and, cause problems. So I can tell you this from a vendor perspective, since I work on the vendor side of the business. This has been a huge concern for us. So any design that we do today, right, is very severely, scrutinized from the perspective of cyber attacks. So following all of the industry standards that, are produced, is an important aspect here, right? But that said, in the electric utility space, we still have, certain, zones. For example, the control center room is something where nothing actually connects out to through the internet. It's all connected through, channels that are built and owned and maintained by the utility itself. So there are specific things like that, but cybersecurity is going to be huge. And we do need to take all the preventive actions. From a vendor perspective, I know we are doing a lot, and the whole industry as such is doing a lot, but nothing is foolproof, right? You'll always, like they say, if you build a tall wall to prevent people from going from one side to the other, a creative guy is always going to build a taller ladder, right? So that's always going to be the case. It's going to be a cat and mouse game. But we need to, as vendors and as software industry personnel, we need to guard against that. Okay. The other question was asset management versus reliability. Reliability is a part of asset management. Okay. So one of the objectives of asset management is to improve the reliability of the system, or to maintain the status quo in terms of reliability. If it is already good, you keep it good. If it is bad, you want to improve it. So reliability is one of those metrics that drives asset management. Asset management as such deals with identifying assets whose reliability is poor or reliability needs, some improvement, and managing the budgets, managing basically the work, managing basically the resources in order to be able to cater to this particular action, right? So asset management is the broad picture. Reliability is, one of the metrics that helps you evaluate that particular asset. So asset management is definitely the broader scope of this whole discussion.
Well, thank you. That was awesome and concise. I think right now we have to be going. We won't be able to take care of any questions. So I believe in the chat room, the email address of Dr. Varadan has been posted. You could send him a private message or more details about what you want to know about the presentation. At this junction, I would like to thank Dr. Varadan once again for taking time out to come and make a great presentation to us all. And moving forward, I'll be sharing my screen.
Yeah,
We'd like to stop sharing.
Sorry, yeah.
Thank you. Yeah, right. Thank you. Just to make some more announcements about our next event. As a student branch chapter, it's an honor for us to collaborate with PMAPS. PMAPS is a IEEE recognized conference talking about probabilistic methods applied to power systems. So PMAPS Manchester 2022 will be holding in the month of June, and we'll be collaborating with the young professional panels in having a career talk session on achieving success in a modern workplace. This will be scheduled for Tuesday, 14th of June, 2022. It's going to be online. And so if you would like to be part of this, if you would like to know more about career planning, how to properly transition from the university to the workplace, you want to ask questions from panelists, technical experts, you could scan this code and or go to our website. Yes, our website, we have more details about this event. Just go to our website, click on next events for 2022, then you'd get more information about this. So so you can also follow us on our social media platforms, Facebook, Twitter, LinkedIn. Give us a like, subscribe, and you get updated on our regular periodic programs, activities, and events. And is there any further question? I think at this junction, we are a little bit past time. We are way past time, because on the flyer it should end 5:30. We are sorry for taking the time out, but we believe that you've been blessed and you've enjoyed the presentation. Yeah. So as Dr. Varadan has said, we would send him the video of this recording. Then if it's fine, then we could post it on our website. Then from our website, you could click on it and watch it on YouTube, right? All right, I'll stop sharing now. And I really want to thank you for your time. Take care till we meet next time. Thank you, Dr. Varadan, for your time once again. All the best. Bye.
Yeah. Thank you very much. I appreciate it.
Thank you so much.
Thank you. Bye-bye.